All right, welcome to our waves extension on light. So we've had the chance to explore a lot of different types of waves, and we've been dealing primarily with mechanical waves. But for this extension, we're going to explore electromagnetic waves in detail. So unlike mechanical waves, electromagnetic waves can travel through both media such as air, or liquids, but they can also travel through space and in a vacuum. So in some ways, that's how they're different from things like sound waves, which require air to travel through. Um, Electromagnetic waves are a form of radiation, and the way we describe that type of radiation is on the electromagnetic spectrum. Waves on the electromagnetic spectrum are classified by their wavelength, which, if you recall, is the distance between crest to crest or trough to trough. And they're typically described in nanometers. So the wavelength of visible light extends from 400 nanometers to 700 nanometers. So I'd like you to pause for a second and think about which of those has the highest frequency. Okay, so the highest frequency would be 400 nanometers with the violet light, as if you remember with our wave equation, as wavelength increases, frequency decreases. So our smaller wavelength here with 400 nanometers would have a higher frequency. And similarly, our red light here would have a longer wavelength but a smaller frequency. So light can move in a variety of ways through a prism. If you think about that Pink Floyd iconic picture where we have light traveling through a prism, light waves actually refract or bend as they change between new media that they encounter. And their speed actually changes, and the angle that they refract at depends upon their wavelength. And if you take a look at this diagram, you'll see that blue light refracts at an angle that is greater than red light. So this is why we see rainbows. As white light from the sun encounters a droplet of water, the water refracts the light into all the various colors of light, and we see a rainbow. Light can also behave in other ways, and all of these different ways that light behave allow us to discover a lot about our universe. So one way that light can behave is through diffraction, and diffraction is the slight bending of light as it passes around the edge of an object. And this is one of those key reasons why we know that light is a wave. So just like if an ocean wave hit a jetty of some sort, and it would bend around that jetty, similarly, light is going to bend as it goes through a small pinhole. And this is really important because it can tell us a lot more about the light from stars. So one thing that we know about stars is if, as we're looking at this electromagnetic spectrum of visible light, scientists have found that different elements that are contained within stars can actually emit light of different wavelengths, and they get a fingerprint of sorts. And so hydrogen on this emission spectrum, for example, will emit this one band of purple light, this one band of blue light, and a few different bands of red light. So if you see this fingerprint and you look up at the stars through something called a diffraction gradient, which is basically a piece of paper with lots of different holes in it, you can tell what types of elements stars are made out of. So the emission spectrum in general is the type of light that can be used to determine the elements that are present in a substance. And if you see these overlapping bands, if I saw both the spectra for hydrogen and for helium, then I could tell that the star had elements kind of like our own star, which is primarily composed of hydrogen and helium. So when we look up at the universe, and we're looking at stars, we can actually tell what they're made out of through looking at light that's diffracted. Another key thing to point out is another behavior of light is how it reflects. So, for instance, when we're looking at the moon, the reason the moon appears as a sliver is because of the orientation of the Earth and the moon in relation to the sun. So it's actually the sun that is radiating the light as a result of fusion between hydrogen atoms that are forming helium atoms. Um, and that light will bounce off the moon, and then it will similarly reflect off and show the Earth. And so at various points in the lunar cycle, depending upon where the moon is, we might see a full moon or a new moon. Now, as you're making your solar ovens, one thing that you're going to need to consider is how the angle at which your the reflectors are going to be on your oven. And one thing to keep in mind is that the angle of incidence, which is where the light rays are hitting, is going to be equal to that of the angle of reflection. So it's kind of like if you're playing pool, you can have an idea of where the ball is going to hit based upon the angles that you hit off the side of the pool table. Similarly, light is going to bounce off at equal angles here. Now, another piece that we can figure out with light is actually what temperature different stars are. So not only do we have the emission spectra where we can figure out what types of elements the stars are made out of, but we can also figure out what temperature they are. So take a look at this candle, and I'd like you to think, as you see these various colors emitted in the candle, which color do you think is the hottest? All right, well, if you guessed blue light, you are right. Blue light is the hottest, whereas red is actually the coolest. And astronomers describe a variety of stars based on what's called the Hertzsprung-Russell diagram, which looks at the luminosity, which is how much light each of these stars is producing, how bright it is, as well as its color. So what they found is that most stars fall on this graph of what's called the main sequence stars. So newer, younger stars tend to be really, really hot, really bright, and more blue in color. And as they age, they tend to get dimmer and they become more yellow or red in color. Now, our star is right about here in the middle of the main sequence spectrum. Our sun is about 4.6 billion years, and in another 5 or so billion years, our sun is expected to become what's called a red giant. So as it ages, instead of getting smaller and more compact and dimmer, it's actually going to get larger. And this has to do with its relative mass and the forces of gravity. So once again, our sun is a main sequence star, and the source of the light that is produced is through radiation that results in fusion reactions that are happening where hydrogen is combining to form helium. And the reason that that's occurring is because the gravitational force, the mass of the sun, is so extreme that it's causing these hydrogen atoms to collide with one another and actually fuse together. We're going to shift gears here for a moment, and we're going to look at another property of light, or actually just of waves in general, and that's a topic known as the Doppler effect. So if you recall from some of our activities that we did in class, we noticed a scenario where it's called the Doppler effect or the Doppler shift, and this is where the change of the frequency of wave changes for an observer that is moving relative to the source. So if you can imagine, for instance, a police siren that's coming towards you, you know just by listening to the sound wave that as it's coming towards you, the frequency increases, and as it's moving away from you, the frequency decreases, even if the siren is moving at a constant rate, or a constant frequency, rather. You can also experience this if you've ever done sit-ups at the beach and you're listening to ocean waves as you're doing the sit-up. It will sound a little bit higher in frequency, and as you move away from the frequency of the sound, it will appear smaller. Now, it will appear longer in wavelength or a lower frequency. So I want us to apply this now to stars. So imagine a star is moving towards us. Would it appear to be bluer in color on the visual spectrum or more red in color? Similarly, think about a star that's moving away from us. Would it appear more blue in color or more red in color? All right, well, if you guessed that stars that are moving towards us appear more blue in color, you are right. And stars that are moving away from us have more of a red color. This is due to what's called redshift. So this is a form of the Doppler effect that we see with visible light, particularly when we're talking about stars in our universe. So when an object moves away from us, its light waves are stretched into lower frequencies or longer wavelengths, and we say that the light is redshifted. In the visible portion of the electromagnetic spectrum, blue light has the highest frequency and red light has the lowest. So astronomers can use this information to figure out the relative motion of different objects in our universe. So I've given you a lot to kind of start with, and I know you have a lot of questions about our universe. And what I would like you to do now is to develop 2 questions that you're interested in learning more about. And in class, you're going to propose those to me, and we're going to have you each do your own individual quest. So for the final, what you're going to be doing is your honors extension is going to be your own quest that will be an extension of the questions that you have proposed for yourself and that I have approved. So I look forward to hearing your questions and helping support you through your future research. Thank you.